Calorimetry. So there are some assumptions that we have to use in calorimetry. The first one is that no heat is transferred out of the calorimeter. So nothing goes out, no energy is transferred to the environment. So we're treating it like an isolated system. Number two, any heat absorbed or released by the calorimeter materials is negligible. So if the container heats up a little bit, it's only a little bit. Dilute, aqueous solutions have the same density and specific heat capacity as water. So your density of any dilute solution, no matter what the substance is, will be 1 gram per milliliter. And the specific heat capacity will be 4.19 joule per gram degree Celsius. So there are two types of calorimetry questions, basic questions that you're going to deal with. One is where a substance is added to water. That substance could be dissolving or it could be cooling down, but water, in this case, is the surroundings. So is the mass in Q equals mc delta T. So the surroundings is the water, and that mass is used in Q equals mc delta T. Another scenario is where you have two solutions are mixed. So it could be an acid-base neutralization reaction or some kind of double displacement with solutions. So both reactants have AQ subscripts. In this case, we have two different initial volumes. We mix them together and we will get a total volume. So now this total volume is of a dilute aqueous solution. Therefore, it is going to be the mass in Q equals mc delta T for the surroundings. So you find the total volume, convert it to total mass using the density of water, and that is the mass that goes in Q equals mc delta T. So here's an example for the first type of calorimetry questions. 9.96 grams of lithium chloride is dissolved in 100 grams of water. So the system is lithium chloride solid dissolving into a solution. There's your system. So delta H equals N delta HX, where delta HX is solution for lithium chloride. So, system, delta H. Temperature rises to 41.3 degrees Celsius from initial 22.2. What is the molar enthalpy? So we want to find this quantity here. In order to do that, we must know N and delta H. We can find delta H because we know the relationship between the enthalpy change and the change in heat of our surroundings. So we're going to start with Q equals mc delta T. This equation refers to the surroundings, so to whatever we take the temperature change of. So it says 100 grams of water at 22.2 degrees Celsius. So this is for water. So the mass is the mass of water, and the C is the specific heat capacity of water, and the delta T is the change in temperature of water. Delta T is always T final minus T initial. So we have 100 grams of water. Specific heat capacity. And the temperature change is 41.3 minus 22.2 degrees Celsius. So the temperature change is going to be 19.1 degrees Celsius. So 100 grams times 4.19 times 19.1 grams cancel, degrees Celsius cancel, and you are left with 8,002.9 joules. So the temperature of the water increased. So your surroundings, the heat content of your surroundings went up by 8,002.9 joules. Okay, so we know that delta H is equal to negative Q. The change in the system results in a change in the surroundings. So delta H is equal to negative 8,002.9 joules. We need to find moles of lithium chloride because that is our system. So 9.96 grams divided by the molar mass. So in this case, 0.23496 moles. So delta H is equal to N delta HX. So delta HS X is delta H divided by moles. Just move this up. So 8,002.9 joules divided by 0.23496 moles. Don't round until the very end. So 34,060.5 joules per mole. Let's put it in kilojoules because we're talking 34,000. We can only have 3 sig figs in our answer, so negative 34.1 kilojoules per mole. There's the molar enthalpy for the dissolving of lithium chloride. Okay, example number 2 deals with the second type of calorimetry question. So 50 milliliters of a 0.3 molar solution of copper 2 sulfate is mixed with an equal volume of 0.6 molar solution sodium hydroxide. These two aqueous solutions produce a precipitate of copper 2 hydroxide and aqueous sodium sulfate. The initial temperature of both solutions, 21.4 degrees Celsius. After mixing in a coffee cup calorimeter, the highest temperature recorded is 24.6 degrees Celsius. Determine the molar enthalpy of change for copper 2 sulfate. So we have copper sulfate solution plus sodium hydroxide solution, and it makes copper 2 hydroxide and sodium sulfate. So here we have a double displacement reaction, and we will need 2 of these. Okay, so our system is going to be copper 2 sulfate because we want to find the molar enthalpy of change for copper 2 sulfate. So that is going to be our system. The entire reaction occurs in a beaker. We mix 2 solutions together. You take the temperature of the solution, so the solutions are also your surroundings. So Q equals MC delta T. That will be the total mass, which will be the total volume, because the density of water is 1 gram per milliliter. Okay, so we've got 50 mils added to 50 mils for a total volume of 100 milliliters. So because the density of water is 1 gram per 1 milliliter, our total mass is 100 grams. And we can do that because that statement right there. So temperature final minus temperature initial is our delta T. So our temperature change is 3.2 degrees Celsius. So now we've got our mass, we have 2 dilute solutions, so we've got our specific heat capacity, and we've got our temperature change, so we can find Q. Once we have Q, we can find delta H, we can solve for delta HX. So Q is MC delta T. We've got 100 grams. 4.19 joule per gram degree Celsius times 3.2. So our Q is 1,340.8 joules. Our temperature went up 3.2 degrees Celsius, so heat was transferred from the system into the surroundings. So it was an exothermic process. So delta H is negative Q. So delta H is negative 1,340.8 joules. Now, in order to solve for delta HX, we also need the number of moles. And it is moles of copper 2 sulfate, because that's what the question asked us to find. So we need moles of CuSO4. Concentration is moles divided by volume. So moles is concentration times volume. We know the volume, we know the concentration. So the moles of copper sulfate is 0.3 mole per liter times 0.05 liters. So we have 0.015 moles of copper 2 sulfate. Now we can solve for delta HX. Delta H is N delta HX. So delta HX is delta H divided by N. So we have -1340.8 joules divided by 0.0150 moles. So 89,386.7 joule per mole. That's a large number, so we're going to change it to kilojoules. So divide by 1,000. We can only have 3 sig figs. So 89.4 kilojoules per mole. So the enthalpy change with respect to copper sulfate is that it releases 89.4 kilojoules per mole of copper 2 sulfate.